Okay, so now we want to get back to and figure out a way to find all the extrema on a closed interval. So of course I can find the derivative, or I can take the derivative. That'll help me. That's what we were doing in the last lesson. Find the critical numbers. We're going to set it equal to 0, and then we're going to solve. And then we'll also set it equal to undefined. So I want to see where my derivative is undefined. Of course, that's only going to happen on special ones like square roots, or if I have rational polynomial functions, ones that have problems because they have exceptions within their functions. Then we're going to take our function and we're going to evaluate. We're going to make that little table and we're going to evaluate it at each of the critical values. And in addition to putting those critical values in my table, I'm also going to evaluate it at each of the endpoints. Because as I just showed you on that graph that I made, if in fact the only place that happens that I get a maximum and minimum dependent upon, of course, the continuous function, it might only be at the endpoints, just like I showed you on the last graph. So I can see here that I get the minimum at the left endpoint and I get the maximum that'll happen over here at the right endpoint. So I need to check those endpoints as well. And then whichever one is the lowest is the minimum and whichever one's the biggest is the maximum. Fairly simple. Okay, so let's look at example 1. So of course the first thing I have to do is take the derivative. I bet you stopped that video and you did that all by yourself, didn't you? Good job. And so I'm going to start by setting it equal to 0 because I want to see when the slope is 0. I would have, of course, a horizontal tangent line. And I notice, I spy with my little eye, that I can factor out a secant. And of course, when I'm solving, if you remember all the way back to solving quadratics, which is where you began with setting things equal to 0, the first thing that we would want to do, of course, is factor. And then I can take each of those factors, and somebody's got to be 0, because the only way I can multiply and get 0 is, of course, if somebody is equal to 0. So I'll set each of them, oops, forgot the theta, equal to 0, and then I'm going to solve. So let's see, remember, this is 1 over cosine. And if you remember, since this is the reciprocal function, if I look at the graph of secant, I don't know if you remember this, but it's a whole bunch of u's. So it was doing this. I took it and I flipped it about those points where it hit 1. So secant never equals 0. It doesn't even get close to 0. The lowest it gets down to is 1 or -1. So this is a no solution. And then on the other side, of course, I'll subtract secant. So I get 2 tangent theta equals negative secant. And then I am going to, what do I want to do next? I don't know. Maybe that wasn't such a good idea, subtracting. Let me think. Pause. Because I can't divide by tangent of theta. I don't know if tangent of theta is 0. Sometimes tangent is 0. I'm going to move it back. And instead, I'm going to turn these into sines and cosines, because my poor little brain struggles thinking about anything other than sines and cosines. Just have more experience with them. And I already have common denominators, so that gives me 2 sine theta plus 1 all over cosine theta. Now I can in fact multiply both sides by something. I just can't divide if I don't know whether or not it's equal to 0. We've seen this in class once before this year. And so I'll multiply both sides by cosine, and of course, poof, that makes that go away. And oh, look, now I have down to a single trig function. Hallelujah, I was getting kind of worried. So I have 2 sine theta plus 1 equals 0. I'll move that 1 over, and then sine of theta is -1/2. And so that means I have to be looking in quadrant 4 in order to take the inverse, and sine would equal -1/2 when theta is -30 degrees, or -pi/6. Except I'm limited by that original domain to the unit circle, so it's got to be 3rd and 4th quadrant, or these